Typically, when we look at problems that involve free fall, we choose our coordinate system so that positive y is up and negative y is down. That means that the acceleration experienced by an object in free fall is going to be in the negative y direction. Typically, we use the symbol g to represent the acceleration of gravity, or the amount of acceleration of gravity, which is 9.8 meters per second squared near the surface of the Earth. Then the acceleration that we use is minus g, the minus indicating that the acceleration is in the downward direction. So this means that when we rewrite our acceleration equations for the special case of free fall, we replace every instance of a with a minus g. If you remember from before, one of the acceleration equations was the final velocity is equal to the initial velocity plus acceleration times time, and we replace the acceleration, the a, with a minus g. And we can do the same for our other equations of motion as well. Now, one thing to keep in mind is that when we do this, g itself is positive 9.8 meters per second squared. So when we're using these equations, you should always plug in a positive 9.8 meters per second squared for the value of g. We've already taken care of the fact that the acceleration is in the downward direction by introducing this minus sign when we plug the minus g in for a. So whenever you see a g, always think positive 9.8 meters per second squared, because the negative of the downward motion has been taken care of already. Another important thing to point out is that objects may be in free fall even when they're traveling upwards. Now, this is a head scratcher. How can an object be freely falling if it's going in the upward direction? Well, remember that we defined free fall as being an object in motion when only gravity is acting upon it. So think about standing at the top of a building and throwing a ball upward. The instant the ball leaves your hand is no longer pushing on the ball. The only force acting on the ball is gravity. And so the instant that ball leaves your hand, it is in free fall, even though it's still going up. It is decelerating as it goes up. It's going slower and slower and slower. And then at the apex of the motion, it will stop for an instant in time and then proceed to fall downward. But this whole motion, even the going up part, is considered free fall and has an acceleration in the downward direction, even though it's going up, because that downward acceleration is slowing it down, and even when it's going up, the only thing acting on it is gravity. So let's look at this, split the motion up into these two different parts. Think of throwing the ball in the upward direction. The instant it leaves your hand, it's still going up and its velocity is decreasing. So the acceleration is minus 9.8 meters per second squared in the downward direction. The acceleration is downward, and so it's effectively nibbling away at your velocity vector and slowing the ball down. So the ball is moving upward, but its velocity is becoming less because the acceleration is in the opposite direction. Then when the ball stops for an instant and turns around and starts coming down, its velocity is increasing. It is getting bigger and bigger in the downward direction, so the ball is speeding up because now the acceleration, that minus 9.8 meters per second squared, is pointing in the downward direction and adding to the velocity. So remember that when you have an object, if the object is not being pushed or pulled by anything but gravity, then that object is in free fall, whether it's moving up or moving down, and its acceleration is equal to minus g, or minus 9.8 meters per second squared. So here on this slide, you can see that we've taken all of our constant acceleration equations and in each case replaced the a with a minus g. Now, some of our equations didn't have an a in them, so they remain the same. So these equations you can use if you are in a circumstance that involves free fall. So now on this slide, we see all of the equations of motion that we've discussed up to this point in the class. We know that when the velocity is constant, when the acceleration is 0, and we are just moving at a constant velocity in one direction, we can say that the displacement is velocity times time. And this equation only works when we have a constant velocity. On the other hand, if we have a constant acceleration, we can say any of these equations apply. And if we have free fall, we can take our constant acceleration equations and replace the a with a minus g. And those equations will apply as well. You'll see that with the constant acceleration equations, we're using delta x, and with the free fall equations, we're using delta y. And the reason that we do that is typically when we have free fall, the motion is in the y direction, the object is moving up and down, and often when we have constant acceleration, the motion is in the x direction, but that may not always be true. If we remember the rocket problem that we did with the Apollo astronauts, they were moving in the y direction, so it would be equally valid to replace any of these delta x's with delta y's if the motion were occurring in the y direction instead of the x direction. So here is another question for you. Let's say we have a tennis player throwing a ball straight upwards. So while the ball is in the air, what does its acceleration do? Does the acceleration increase, decrease, increase then decrease, decrease then increase, or does the acceleration remain constant?